are going to record the video. So later on, I'll move both of those onto my external hard drive, take it home, and then fuzz with it after that. So I can double check a little bit just to see whether it looks like it is recording or not, because I cannot really. I suppose I can play it too. Look into the D drive, and there should be 2 files, and they should be growing as well. So here's the MP4, which is the video, and here's the audio. And you can see, interestingly, the video is growing slower compared to the audio one, which doesn't seem right to me. Okay. I guess there's only one way to really check it, is to play the video and see if it is.
Why not copy the platform?
This is recursive.
Yeah, it's not recursive.
Yeah.
Isn't it?
No, it's not.
Inception.
I think the video language.
Okay, well, we'll just
Why don't you go back and then forward again? It'll kind of like refresh it, and then you'll see it.
Well, it is recording. The file is getting bigger. It's just that the encoding may be fuzzy. It's growing. Yep. All right. So we'll start with the practice test, and then we'll move on to the actual test, or we can just go straight to the actual test too. The actual test from the previous semester.
I was about to say, I thought that was next week.
The actual, yeah, that's Tuesday.
Had me worried.
Well, you didn't see me bringing a pile of papers. So
Yeah, it's up there, and we gotta do it in our notebook.
Hey, well, maybe you're like Fox. Forgets it and just gives everybody A's.
Yeah.
Does he?
One time. Yep.
Oh,
That'd be awesome.
That's on recording.
that would ruin my reputation. Okay. All right, so let's go ahead and go back to exam 2. And we'll start with the actual exam. So exam 2 is right here. Okay. So this is the actual exam 2 from last semester. Yep.
You have the microphone, so it always gets quiet when you walk away from that.
Well, you remember what I said, when things don't work, they don't work at the same time. Yeah, nothing ran out of battery again. I have already asked for rechargeable batteries, but obviously nobody has acquired the batteries yet. And they have, I mean, obviously they have not heard of Amazon Prime. Yep.
You can borrow mine.
Do you mind?
No, I don't mind.
Okay.
It's better for the recording.
Okay.
Everybody.
Thank you.
Haven't you ever seen the Apple Jacks commercials? Everybody's a winner one.
That's an oxymoron.
That was like 4 or 5 years ago.
Yep, definitely working.
Those things never die.
I personally don't think
Those
it's
things
racist.
never die.
They weren't, making fun of anybody.
All right, so here is your
just
actual
making
exam
people
from last
as people.
semester, or
Nothing
last
wrong.
the last time this class is offered. And by the way, this class is going to be offered every semester from here on, so it will be offered again in the fall. Not that I'm implying that it will be I'm just saying that it will be offered every semester now, so it won't be as impacted as this class. This is a pretty big class. All right, so question number 1, you can see it is very much the same or similar compared to the practice exam 1, which we spent a lot of time on Tuesday. But this one is easier because when you read the question, it asks explicitly, express the chances of exactly 2, but any 2 students having the same birthday, and then later on it also asks and say, and everybody else has a unique birthday. So that actually makes the problem a lot easier to deal with. Because now we know out of the 30 students, there are only 29 exact different birthdays. So somehow you have to distribute 29 birthdays amongst 30 people. And we need to figure out the number of outcomes that will fit into that description. The instruction says right here, first consider a class of 2 students. What are the chances that both students share the same birthday? What do you think? With only 2 students, the chances of both students having the same birthday is going to be
2 out of 365.
okay. The first student can choose any day, right?
Yes.
But the second student has no choice anymore because it has to be the same birthday. What about the possible number of outcomes? Because I want you guys to analyze the problem using those terms, because that's in general how we solve problems. Well, when you look at all the possible outcomes, the first student has 365 days to choose from. When you look at the second student, he or she also has 365 possible days to choose from. So the denominator is 365 squared, where the numerator is 365. So that means the solution, the chances, is 1 divided by 365. Is that okay? All right?
Is that where the entry came from last time?
Correct. But last time I was trying to solve a different problem and incorrectly making the assumptions because it didn't take into consideration of all the other possibilities. So that's why the number is a lot smaller than it should be. Okay, so I got my document camera ready. And hopefully this will still work. So now I have 3 instances of VLC running.
You gotta be careful, it might crash.
Nah, it's VLC, it's open source, it doesn't crash. Bad things only happen to proprietary products. Okay, so let's take a look here. Yep, we see the device. Let's play. Oh, we go. Yeah, that works.
Woohoo!
Okay. Do you know why it's doing this?
Because we didn't mute it.
Because when I played it.
You got it.
Stop talking. Because this thing has its own mic. When I play it, I did not say okay, no audio, so it's echoing because I said play, so it just goes okay, fine. I will just repeat whatever the microphone has, but there's a certain lag to it, so that's why it sounds like an echo.
You should just turn off the first mic then if you can use the second mic instead of having 3
No, you
different
should
VLC.
mute the screen, right?
That way you're not picking up an echo on the other actual recording.
It'll save you
Put it
the
to
editing, I guess.
the other VLC.
Well, the other one is still going, it's still recording, so I don't want to mess around with that one.
When you splice them together, can you splice the video without the audio? Like,
Yes. This one is completely separate, by the way. This one is just completely separate. Okay, we want it to be higher so we can see the whole thing.
The refresh rate is slow.
I know. And it's also not in the right direction, but I can fix that. So we go to Tools, go to Video Effects, go to Geometry. And I think we have to rotate by 270 degrees. 180? Yep. Alright, so we just have to that looks about right. And we just need to autofocus. Nope. There we go. All right. So that part is done. Okay, now I just need a pen or pencil. There's one here. There we go. And now I have no idea what I was supposed to use it for.
But we got it.
So we got this working, yep. All right, so we need to look at the numerator and the denominator. So this one does have a little bit more lag.
You could snap them on both sides, that way you have both of them displayed.
Oh, okay. Yeah, but I think this will show better because now we have more area just for the whiteboard, and then we can flip back and forth. Okay, so when you're looking at the chances, you are looking at a fraction. You're looking at a numerator and a denominator. The numerator is basically telling you how many outcomes are of interest to us. So in this case, it will be the outcomes where both students in the class of 2 having exactly the same birthday. So we need to count how many outcomes we have fitting that description. The denominator is easier because that's just listing all possible outcomes. Since we have 2 students, each one has 265 possible days to choose from as a birthday, then the actual number is going to be 365 times 365. So that becomes the denominator. On the top, the first student can choose any one day out of 365. The second student can only choose one. It has to be the same as the first one. So that basically limits, the possible outcomes of the numerator. Does that make any sense? The other way to look at this is to say, okay, since we only have 2 students and they must have the same birthday, then they can all have the same birthday, which is the first day of the year. They can both have the second day of the year. They can all have the third day of the year, and so on. But there are only 365 days in the year, so that also tells you that the total number of interested outcomes, or the outcomes that we are interested, is 365. Okay? So that's the answer to the case where you have a class of 2 and you want to have exactly 2 students having the same birthday. So just to finish this, it's 1 divided by 365. And according to this instruction, it says, second, consider a class of 3, express the chances of any 2 out of 3 students sharing the same birthday. Okay? Now this one is a little bit more complex. Okay, the denominator is still pretty easy because 3 students all having independent birthdays means that we have 365 to the power of 3 as the possible of outcomes. Okay, so the denominator is pretty easy to figure out. The numerator is a little bit harder. Okay, because in first glance it is easy because the first student has 365 choices to choose from. The second student, who must have the same birthday as the first student, only got 1 day to choose from. And then the third student, which cannot have that very same day, has 364 days to choose from. So that seems pretty easy. But this is not actually the answer. Yep, go ahead.
Oh, never mind, go ahead.
Okay. No, go ahead. I want you to.
Okay, I'll try.
Okay,
So
okay.
It's 365 times 364 times 365. Because like the second one, you're pinning him to a different day, and the third one can be either of those 2 days or any other day.
That's one way to look at it, but there's another way to look at this too. 365 times 364 is how many ways we can choose 2 days out of 365 days. Does that make any sense? Okay. But I can assign those days to 3 students in various ways. Okay. Now, let's think about how we can do this. We got 3 students. Okay. So let's say we have student A, B, and C here. Okay. We can have A, B having the same birthday. We can have B, C having the same birthday. We can also have A, C having the same birthday. In other words, there are 3 ways to arrange the 2 dates that we have picked amongst the 3 students. Does it make sense? Okay. So that means the number that we have, which is 365 times 1 times 364, is only accounting for one of these 3 cases. So that means we also have to multiply this entire number by 3. But I'm just expressing it as 3 here because it's without generalization. But at some point we want to generalize and go like, oh, what if we have a class of 20 people? How do we express that portion? Yep?
So is that 3 at the end right now? Is that like 3 choose 2?
It is because of 3 choose.
Those are permutations. Well, it's not permutation, which order doesn't matter. So it's called
Permutation is when the order is important, and it is important in this case because we have student A, B, and C. So who gets which birthday is actually important.
So wouldn't the order not matter because A and C and C and A is in a different configuration? Like those are both lumped together, it's the same. So it's in combination.
we'll take a look at the next case too, because as the number goes up, then it becomes even more clear. All right, so the next one, so we can keep doing this, to make it more general. We'll take a look at the case when there are 4 students in a class. Okay, so we got 4 students in the class. The denominator is 365 to the power of 4. That part is simple. The numerator is going to be 365 times 364 times 363 times 1. Because out of the 4 students, 3 would have unique birthdays, and 1 has to share with one of the other students. Is that okay?
This is for if we had 3 choose 4, or 5?
Well, this number, the 365 times 364 times 363, is let's see, that's a permutation. Okay, that's a permutation of choosing 3 things out of 365 things. But then we have to multiply something here, because now we have to choose which 2 students share the same birthday. Yep.
But that's assuming that the other 2 students don't share that birthday.
That is correct. That's a part of the description in the question, is all other students have unique birthdays. So there are exactly 2 students in the class having the same birthday, and everybody else have different birthdays. Okay. So out of 4 students, how many ways can you group which student has the same birthday as which other one? Okay, so you have A, B, C, D. You have A, B, B, C, C, D. You have
16.
No, not 16. Okay, so you have 8. This is not very systematic. I should have done it in a more systematic way. Then you have BD, and then you have. It's 4 choose 2 basically. It's C42, C42. And am I missing anything? AC. Okay, so AC. Okay, 3 starting with A, 3 starting with B, 3 starting with C. Okay, so that should be it. But the combination of 4, 3, or 4 choose 2, excuse me, 4 choose 2 should come up with the same number. So this is 4 factorial divided by 2 factorial times 4 minus 2 factorial. So that's 4 factorial is 24, and 2 factorial is just 2. So we have 2 times 2 here, and this turns out to be 6. Okay. So now we know that we also have to multiply C, and then 4 is the size of the class, and then 2 is because we want 2 people having the same birthday.
So it's P times C all over 365 to the n power. Because we have
Right.
to the right. That like the general form.
Yep. So the general form is you still have this portion here. Actually,
Which is P. It would be like in this case it would be P of 365 choose 2.
The summation of 365 minus I.
yeah, but
starting
I'm
at
just
0,
thinking
going
whether
okay.
I'm still missing something with the 365 times 364 times 363, which is a permutation.
Yeah, which is P. And then you have a combination right next to it.
Yeah, that's correct. Permutation is actually correct. So we have P 365N, and then C 4, oops, not 4, N2, the whole thing divided by, okay, this just happened to my pencil. Yeah, as I said, if things have to go wrong, they all have to go wrong at the same time.
Want to raise the 4s?
Yep,
It's gonna rain tonight as well.
that is
It's
true.
raining right now.
Is it?
You tell
Oh.
me.
Yeah, my lead broke too.
Definitely pouring right now.
Okay,
Do
all
you
right.
need to borrow some pen?
No, I just need to borrow some luck.
I was about to say that.
And then we'll get to lottery as well later on.
Don't buy any
Just
lottery.
don't.
Yeah. No. I would buy one, and you guys have to buy everything else. Because the one that I buy is guaranteed not to win anything. So if you buy anything else, then you have a slightly better chance of
But if
winning.
you buy
Or-
a lot more tickets, then we buy the remaining.
You can pay me to buy a lot of tickets. Yep.
Does C4 choose 2?
It's not, it's n, it's supposed to be n. N choose 2, because you have a class of n, and how many ways can we choose the 2 people sharing the same birthday?
And 365 can, the power bank.
I wonder why it's not showing up here. Is that okay? Is that better? Okay. So that's the actual answer to that question. Shall we move on? Yes. All right. So that's question number 1. Question number 2 does not apply because we did this already with our first exam, which is proof by resolution. Okay, so we don't have to do this one. In the final exam, we can review this, but for the second exam, let's skip it. So moving on to question number 3. Question number 3 is proof by induction. Okay, so let's take a closer look. I want to zoom in a little bit more, because I really just need to show you the equation that I want to prove, and then we'll work on the actual proof. So this has to do with summation. Okay, if I want to add 1, 2, 3, 4, what is the sum of 1, 2, 3, and 4? Well, 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10. Okay? So the question now is, in general, if I have something like this, okay, let's go to the next page. And by the way, there was another meeting for the new building, the building that will replace all the liberal arts classrooms, and so it's positive. Computer BCS ends up with 4 classrooms and 5 labs. Math ends up with 8 classrooms, and then there will also be physics, engineering, and astronomy classes too in the same building. So it'll be kind of fun. Yep.
I have a question with question number 1.
Uh-huh.
The permutation should be like 365 choose 1 and minus 1.
Choose n minus 1 because there's one sharing a birthday with everybody else. That you're correct. Should be n minus 1. Yep.
Why is that one different from a binomial distribution, the last question?
Which one?
The birthday problem. We didn't use binomial distribution in that one.
You didn't use binomial distribution.
Why is that? It seems like a valid target for the binomial distribution equation with the where you set p the probability to just 1 out of 365.
That's for when the class has 2 students, then the chances of that happening is 1 divided by 365.
Okay. When can you use binomial distribution?
When you flip coins.
Because the probability
There are
is
2 outcomes per event, and then you're looking at a string of events. Yep. Okay, so I'm not sure. Can you guys read that? Is it okay? Okay. So we want to figure out what is 1 plus 2 plus 3 plus 4 all the way to n, and it has a closed form already, and most of you already know the closed form of this, which is n times n plus 1 divided by 2. Okay. So we say, okay, we kind of know this already. The question is, well, do you know that it works only up to a certain number of n, or do you know this is true for any value of n? There are several ways to prove this, but we want to prove it by induction. Okay? So let's take a look at proof by induction and see how it works. Does anyone remember how proof by induction works? There are 2 steps to it. Yep, go ahead.
If it's true for k, then it's true for k plus 1.
That's called a step of proof by induction. There's one more step to proof by induction.
Set the base case.
There's a base case you have.
There's a base case, very good. So there are 2 steps. There is the base case, okay, base case, And then there's also the induction step. Induction step. Okay. The base case is basically the end of recursion. If you look at this as a recursive algorithm, this is the case where you don't have any recursion. This is the one that you say, oh, this theorem is true because the n that we want to deal with is trivial. Okay? So which n do you think is going to be trivial in this case? Okay, when n is 1, it is trivial. So let's see why that is the case. So we are saying that 1, oops, I let it broke again.
Let me know when you run out.
Let me see if I have a ballpoint pen.
I think you have one.
Yep, I got one. Okay, thank you. And we'll see whether it works. Yep, that works.
Probably just as well as I break mine.
Okay, so 1 is, is 1 the same thing as the summation of I equals to 1 to 1? I. Would that be okay? The summation of I going from 1 to 1, I is 1. Okay, we know that. What about this one here? Because n is 1, so we have 1 on the outside, and then we have 1 plus 1 here, and then the whole thing divided by 2. Does that equality hold? Well, guess what? We just got our base case proven. So when n equals 1, it is true. Is that okay? So now the induction step, okay, what does the induction step do? We assume that it works for case k. Then we want to say that will imply that it works for k for the case k plus 1. Is that okay? So let's check out what does it mean in this case. So in this case, the induction step is basically saying, assuming the theorem is true, the theorem is true for n equals to k, this implies the case for n equals k plus 1. This is what we want to prove, okay? Making the assumption that the theorem is already true when n equals k, we need to prove that based on that assumption and the usual algebra, that we can also prove that the theorem is true when n equals to k plus 1 as well. Okay? That's the induction step. So let's see what does it mean when we say it works for the case when n equals k. Well, that means for case n equals to k, it simply means when you have a summation of I equals to 1 to k of I, then it is the same thing as k times k plus 1, and then the whole thing divided by 2. This is the result of the assumption that it works for the case when n equals k. Is that okay? So now we want to say, okay, knowing that this is true, what can we do about the case where n equals to k plus 1? So we start with I goes from 1 to k plus 1 in this case, I, okay, because that's the term that we are adding. And we want to basically end up with k plus 1 times k plus 2, and then the whole thing divided by 2. That's our destination. So we want to look at this and go like, maybe I should restate this whole thing so that it makes use of the premise of when n equals to k. Well, that's not too difficult, because this whole thing is just, okay, let's break it up so that we have the first chunk of the summation of I equals to 1 to k only. Then we have one extra term left, right? That one extra term left is just k plus 1 on its own outside of the summation. Is that part okay? I'm just breaking the summation apart so that it accounts for all except for one of the terms and separate that term out. But we already know the assumption is the theorem is true for n equals to k, which also means the first part here can be rewritten as k plus 1, and then the whole thing divided by 2. That's because of the assumption. Okay. And then we just add the other part here. Okay. So now we try to have the same denominator by multiplying 2 to the part on the right hand side. So now we can combine these two. So now we have k plus 1 plus 2k plus 2, and then the whole thing divided by 2. Is that still okay? All right. So now we have to rearrange the terms a little bit. So it becomes k plus 1 times the whole thing times k plus 2. So what we do is we take all the terms out. Okay, let me see what is the best way to do this. That works. Well, it's not aligned. That's better. Okay. So now we can start. Yeah, go ahead.
If you have less steps, we just need to get to 255 to k plus 1. So if you keep 2 multiplied by k.
Oh, right. You can factor. You can use the factor too. Yep. Okay. Good idea. Okay. So let's go back to the previous step. Okay. That's what you meant. Yeah. So keep k plus 1 together. So now we have the factor of k plus 1. Now we can say, okay, k plus 1 is one factor, but then k plus 2 is coming from this k and this 2 here. The whole thing divided by 2. But that is still not looking like the theorem. Well, maybe this will help. K plus 1 by itself, k plus 1 in its own parentheses. That makes it clear. So that's the end of the proof of the induction step. Once you have the base case and the induction step, then the whole thing is proven. We do okay so far with proof by induction. Okay, here comes the question. Are there ways to combine proof by induction and proof by contradiction? Yep, you betcha. Those two are quote-unquote orthogonal. So in the case of proof by induction, the induction step itself can use proof by contradiction sometimes. All right. Yep.
Can you say one more time how the final solution relates to the general form that we got at the beginning?
Sure. The general form is we want to look at, okay, it's still on the projection. This is where we start, right? Which is the case where n equals to k plus 1. The general form is when you have a summation of I going from 1 to n of I, then the result should be n times n plus 1, the whole thing divided by 2. So in this case, our n is k plus 1. So that means we want to get to the form where we have k plus 1 by itself, and then in parentheses there k plus 1 plus 1, and then the whole thing divided by 2, which is what we ended up with.
Okay, sweet. Oh, okay. I got you.
So that's why this is the end of the induction step. Okay. Any other questions about proof by induction? No questions about proof by induction? Okay. Yep.
The other one, the one that you gave as a practice test, uses.
Factorial.
Yeah, it uses that little. I don't know what the name is.
The pi it's called a big pi notation instead of the big sigma. Pi is the product of those individual terms, and then sigma is the sum of those individual terms.
I don't know if you want to. That one was a little bit more. I don't know if it was more interesting, more involved in this one, but.
That one is easier, actually. Yeah.
I looked at it and I
Okay.
Yeah, I have a question. So, when you went to the second sheet, you combined like terms, then you factored it?
Actually, okay, forget about this one. This one is not needed.
Yeah.
So I went straight from this one all the way to here.
Yeah, and then how'd you get on the second one?
How do I go from here to here?
Yes.
I factor out k plus 1. Because you can see that for this particular summation, the two terms for that summation, they're both products of something times k plus 1.
Oh, okay.
So I factor out the k plus 1, and then the k coming from the left-hand side, and then the 2 coming from the right-hand side, they become its own term.
Yeah, okay.
Yeah, it's the reverse of using the distributed is reverse distribution or factoring.
Thank you.
Mm-hmm. Yep.
For the base case, do you use the number that's the summation is starting from? Like whatever the summation
From
is?
1 to 1.
Well, it's not always a summation, is it?
Hmm?
It's not always a summation, but you can use whatever number's easy, right?
The base case has to be in the form of the theorem that we are proving.
Yeah, but we picked 1 for the base case.
Yes.
Does it always happen? Why 1?
Because 1 is the smallest value that you can choose for n. Now, obviously, you can choose, okay, let's say 3, okay? You can choose a base case of 3, but if you start with a base case of 3, what happens to when n equals 1 and when n equals 2?
The theorem doesn't work that way, does it?
Well, you can still separate those out as their own cases, but then you're adding extra steps that was not necessary. But if you start a base case with 1, which is the smallest value for n anyway, then you're done. Yep.
What if, why did we choose 0 as a base case?
Summation doesn't work.
Because the summation starts with I starts with 1 as an index, so you can't put a 0.
But we set that where I equals 1. In the theorem, it doesn't say that would be
No, the theorem says I
It should have 0.
Yeah, show the theorem.
0, that would work as well. Let me see. Okay, if you start with a 0,
We prove that it's
Okay.
So you have to find a domain, right? You have to figure out what is the beginning.
yeah, 0 would work too.
Yeah, but what I'm getting to is, let's say the theorem says 2n equals 3n, right?
Say again?
Because the theorem is problematic. Let's say the theorem says 2n equals 3n, right?
Well,
Let's just,
that's only
we're
true.
gonna do like a different problem.
Okay.
It says 2n equals 3n. We say, prove by induction, and we start with 0. The 0 satisfies it. 2n equals 3n is satisfies that. But it doesn't mean that it's true for 0 plus 1, which is Rn plus 1.
Okay, let's take a look at that one. Okay, so let's look at one of the fallacies of proof by induction. Okay, well,
Can we
it's
move
a
on to
fallacy.
number 6 instead?
Let's go back to this one after we finish all the other ones, because that's a good point, because we do want to make sure that we go through all the questions.
I just have one more question on question 3.
Huh?
I have one more question, it's really fast.
Yeah, go ahead.
So basically I noticed that it's basically the same as the original case, but all you did was plug in k plus 1 for each k value. So couldn't you technically just, instead of like saying I plus k plus 1, you could just say that k itself is k plus 1 now and plug it in for each value at that point? Because your answer is k plus 1, parentheses k plus 1 plus 1 over 2,
Yeah.
which is the same as the original one, but the only difference is now is that you substituted k for k plus 1. So
Correct.
in a way, instead of going through all the steps, you could have just said like, oh, let's just plug in k plus 1 for all the values and then get the same answer, or is that wrong?
I don't understand what do you mean. What do you mean by plugging in?
From the previous step.
Yeah.
The previous step plugs it, okay.
But that plug-in is the purpose of the proof. He walked through all the steps so that you can see.
Oh, it's the same. Oh, okay, I got you. So that's the proof that you show. I got you.
Okay. So are we good on that one or not? Okay. Let's go through some of the other ones first, and then we can go back. Okay, question number 4 is where you turn a non-recursive algorithm into a recursive one. So in this case, we have find maximum. The first parameter A is an array, or we can look at it as a pointer, but in C, it doesn't make any difference. Okay, a pointer is an array. The second parameter is n, which is the number of elements in the array, because in C and C++, when you pass an array, the array itself does not contain size information, and you have to pass it as a separate parameter. We have a local variable max, and then we have a local variable I. This is supposed to be equal to. I have no idea what happened to all the equal to symbols, but they are basically not represented as equal to. So this is supposed to be equal to This is supposed to be equal to, this is supposed to be equal to. So the algorithm itself is nothing really tricky. It's just finding the maximum value of any particular array. So are there any questions about find max itself as an algorithm that is non-recursive? Yep.
On the third line, what is max minus a?
That's what I said. It's supposed to be equal symbol.
Okay.
Yeah. Somehow it didn't get rendered correctly. I blame it on Windows. I don't know. If you guys have a computer right now, you can open up the PDF and see if that's the same problem.
Nope.
No?
It shows that it's good, yeah.
So
It just doesn't
this
like you.
installation of Windows. As I said, when things go wrong, everything has to go wrong, including font problems. Yep. Yeah. There's no return statement. I forgot to return max in the end. Okay. You're supposed to return max at the very end. Okay. So the algorithm itself is iterative. So now the question is, how do you turn this into a recursive subroutine? Okay. What do you think? So the question, this is your part. This is what you need to do. Re-implement find max recursively so that the original problem is broken into two approximately equal size sub-problems. So it's not just recursive. It has to break it up into about the same size of problems. How would you do that? Yep.
I think some base case would be so you find a null character.
Okay.
And then you would just return like just increment by 1 every time you go back up.
Okay, but if you increment by 1, that means you're not separating, you're not breaking up into two about the same size problems. You're not having the problem. Yep.
You could do two function calls, two recursive calls.
Yep.
You send one half the array, and then you send the second half the array at the same time.
Yep. We'll do it. Okay, so let me just kind of write here. So we have int. Okay, this is, the font is too small. Stop it up. There we go. Okay, so find max, we still have a const int star a, which is a pointer to a const int, and then we have int n as the second parameter. Okay, so we handle the base case first. Okay, so in recursion, the base case is the case where you do not need to do any further recursion. So that would be the case when n equals to exactly 1, right? Because when you have exactly one element, then you already know what is the result. So just say int max here, and then we just say max is, well, the only element. Well, the only element has got to be a bracket 0, because you're given an array, and you say the array only has one element, so the only element is now the maximum. Okay. So what do we do if that is not the case?
Send the next element back.
Break the array in two.
You have to break the array. Okay, so very good. You have to break the array. So we'll say,
We need two find max calls.
well, we'll need another local variable. So we'll say, x here. And then we say x equals to find max. Okay. Now here's the trick, that you can do easily in C and C++, but in some other languages you cannot quite do this. Okay. So this one, the first one is going to be a, which is the pointer, and then you just say the number of elements is going to be n divided by 2. And because n is an integer, n divided by 2 is already the floor of the actual number. Okay, because it's an integer division. And the parentheses are not exactly needed, except for emphasis purposes. Okay, so you have this number, and then you also have to look at the other number. I will just reuse max here. Find max. And this time you have to look at the second half of the array, which is going to be starting with a plus n divided by 2, and then the number of elements is also going to be n divided by 2, sort of, but not exactly, because what if n is not an even number? Yep, so you have to do it like this just to make sure that we catch all the elements. Is that okay? So we break it into about the same size. So now you have to look for one particular question is, what if, is it possible for us to end up with an n or the length being 0?
You get an alternative?
No. I'm worrying that when we do the recursive call, can n divided by 2 be a 0? Yep.
I had another question. I wanted to know. Yes, I can. But I wanted to know why we don't call size of int here.
Size of int?
Yeah. Why can we just add to the pointer? We don't have to tell it how.
That's pointer arithmetics. Okay, so in CISP 360, they may or may not have talked about this. Okay, so when you add 1 to a pointer, you are actually moving to the address of the following element. You're not adding 1 to the strict address itself. You're basically you're computing the address of the following element. So it will automatically take into account the size of the item, or the size of the type of the array. So if this is an array of ints, it will automatically skip an integer if you just add 1. If you add n divided by 2, then it will be adding, in terms of byte addresses, it will be adding n divided by 2 times the number of bytes per integer. So that part is automatic.
You would only need to do that if you're doing dynamic memory where the type is void, right?
This will work as long as it is not a void type.
Yeah, so
because a void has no size.
If you were using malloc or something, then you would use size for your pointer arithmetic.
No, it wouldn't be a problem, because even if the array itself were allocated by malloc, by the time it gets into this subroutine, a as a parameter is already having a type of it is a pointer to const int.
Oh yeah.
So by this time, the concept of having a void pointer is completely irrelevant, because it would have been casted already in order to just to make this call. Yep.
But by adding 1 to integer pointer, will it add 4 bytes to it?
It will add whatever the size of an integer is.
Okay.
Yeah. So it takes care of the size, automatically. I can see how you guys don't like to use pointer arithmetics. So let's restate this using another way.
No, I get it now. Fine. We're clear.
No, I insist.
Okay.
How's that?
Yes. Okay. Much less simple.
Well, I mean, it's the same thing in C, okay? It really has no difference between what I had originally and this form. It really is literally the same as far as the compiler is concerned. Yep. Yep.
I'm still confused on why you need to subtract n divided by 2 from n.
What if n is 3? If n is 3, n divided by 2 is 1, and n divided by 2 is 1, so you have one element that is not taken care of by either call, so you have a problem in that case. Okay, but it's not done yet, because we still have to look at x and max and see which one is actually larger. So that part is pretty easy to do. We just say max is, if max is greater than x, then it is itself, otherwise it is x, or something like that, greater than or equal to. There we go.
Could you use a mod instead of the division?
No, you cannot use a mod in this case. You do need a division. Because a mod looks at the remainder, and the remainder of division by 2 is either a 0 or a 1.
And then you know either to, if it's a odd or even.
But this takes care of it too, because n divided by 2 is, in the worst case, just short by 1 with one of the halves, and doing this will take care of that. Yep. So I remember the original problem, so now we say return max here.
Do we have to use ternary operator, and can we use if statement?
If you want to, you can use if then else. That's just lengthier.
Yeah, but it's more clear.
Is what?
It's more clear.
Is more clear. To some people, it's subjective. Any other questions about this particular problem? We just turned something that was not recursive into something that is recursive. And the interesting thing is this will also fit into the master theorem discussion, because the master theorem discussion requires the recursion to fit in a particular form. This actually fits into that form. When you look at the time complexity, do you think the recursive version of this algorithm, is it worse or about the same as the original algorithm? We're not looking at the coefficient. We're not looking at the actual amount of time. We're just looking at the Bechdel notation.
Seems like it'd be about the same.
It is the same. Yep. Because if you look at the actual number of comparisons, this will end up doing the same number of comparisons as the other one. All right. So we are done with question number 4. Moving on to question number 5. Question number 5 is the lotto problem, and this time I chop it down into many different smaller steps. So this way people can get partial credit. If you can get the first few steps right, you still get partial credit. All right. This is Fantasy 5. 5 lucky numbers from 1 to 39. So we have 110 tickets matching 4 out of 5 numbers. 3,151 tickets matching 3 out of 5 numbers on this particular date. So step 1 is to derive a formula for the total number of unique tickets and call this X. Okay, so let's see how we can do this. Oops. Just passed it one. Okay, we got 5 numbers. 5 lucky numbers. Each one is going from 1 to what? 39 again? Okay. So let's check out the math, but I need to look at the question first just to make sure that we get the numbers right. Okay, yeah. 5 numbers, 1 to 39. So the first question is, what is the total number of unique tickets? Which is not the same thing as what is the total number of tickets, because Lotto can issue duplicate tickets. So there can be 2 tickets with exactly the same numbers. All right. So in this case, it's 39 times 38 times 37 times blah, blah, blah. Okay, since there are 5 numbers, we can just work it out. 35, yep. But that's not the correct answer. This is permutation. In other words, if I were to use this number, that would imply that the ordering of the numbers matter. Does it really matter? No, it does not matter. So that means we have to divide it by the factorial of 5, but there's also a name to call that. Combination. It's combination. So if you just say C39.5, that would be X for step 1. Is that okay? Does everybody see why it is not just a permutation, but you have to make sure that you remove the duplicates because of the same numbers but arranged differently? Yep.
What was the question again?
The question is, step 1, derive a formula for the total number of unique tickets.
Okay.
So the answer is, it's 39 choose 5, or C39.5. Yep.
When you say unique tickets, do you mean the total number of possible outcomes, or do you mean the total number of all outcomes?
That's all outcomes.
All outcomes. Yeah.
Okay, step 2. Step 2 is to derive a formula for the total number of unique tickets that match 4 out of 5 numbers. Okay, and call this U. Okay, so we'll take a look at how do we compute 4 out of 5. So for a ticket to match 4 out of the 5 lucky numbers, how many ways can we choose 4 out of 5 lucky numbers? I think I just told you the answer. Right? The word choose. Yep. So U starts with choose, okay? 5 out of 5, choose 4. Okay, so these are the lucky numbers. But since it is only having exactly 4 lucky numbers out of 5, whatever is remaining is one of the non-winning numbers, okay? So that means how many ways can I choose the non-winning numbers? Now in this case it's very easy because we only get 39 numbers to begin with. It cannot be one of the 5 numbers that are the lucky numbers, so it has to be 34. But that's not a very general way to look at it, because even though we know it is 34, okay, but that's not a very useful way to look at this, because the better way to look at this is to say, how many ways can we choose one thing out of 34? Now that makes it more general, because once you know this pattern, you just have to remember this is the number of lucky numbers, which is fixed by the rules of the game, okay? It's always going to be 5. This number is always going to be the total number of numbers, which is 39, minus the number of lucky numbers, which is 5. 39 minus 5 is 34. That one is not going to change either. Then what can change is how many numbers are you matching versus how many numbers are not matching. But we know these two numbers have to add up to 5. So that means now you have a general equation of how to figure out all the other the other numbers. Okay, so let's go back to the question. So we are done with number 2. We have U. Number 3 is to derive a formula for the total number of unique tickets that match 3 out of 5 numbers and call this V. Okay, but since we have this general equation, or at least an understanding of the general equation, then we can just say, oh, okay, it's about the same thing. There can only be 5 lucky numbers, but we only need 3 to be matching in this case. And out of the 34 numbers that are not lucky numbers, now this time we need 2, because we need 3 plus 2 to equal 5. Is that okay? Sorry? Question? No? Okay. So now we have X, we have U, we have V. And then in step 4, derive a formula for the ratio of unique tickets winning 4 out of 5 of all unique tickets. Well, that's just a ratio. Okay, so this is step what again? 1, 2, 3, that has to be step 4. So step 4 is just a ratio of U divided by X. Because X is representing, the total number of unique tickets, and U is representing the number of tickets where 4 out of 5 lucky numbers are matched. And you don't have to give me the exact number, I just need the equations or the formula. Step 5, I think, is the same thing but applied to U. Yep, there we go. Step 5 is to derive a formula for the ratio of unique tickets winning 3 out of 5 numbers. So let's go to step 5. It would just be V divided by X, just like that. And step 6, based on the exact number of sold tickets matching 4 out of 5 numbers, derive a formula so that we can estimate what is the total number of tickets sold. Okay, so that means we have to relate this number, okay, this is step 6, with the actual number of tickets sold where 4 out of 5 numbers matched. So in this particular case, we have 110. So in order to figure this out, we have 110. Okay, so here's the equation. 110 divided by n, where n is the total number of tickets sold. This is the ratio that should match this ratio. Is that making any sense?
What is X again?
X is the total number of unique tickets. It's done on the top here. Okay? So the ratio of 110 divided by n should be about the same as the ratio of U divided by X. But once you have this ratio and you want to figure out what is n, you can just go ahead and say n equals 2, 100, okay, let's see. Yeah. So it would be 100 times X divided by U. 110. Okay, there we go. And that's the final answer. You don't need to give me the actual number, you just need to give me the formula for the value. And if you get the formula right, that counts.
Where did 110 come from?
The 110 comes from the fact that there were exactly 110 tickets matching 4 out of the 5 lucky numbers on that particular date. So that's about a year ago.
The same ratio should be true for 3,001 or so.
Except it did not. You know, these are approximations, so we are just using approximations here. You can actually try to figure it out and just figure out the actual values and see whether they come out to be about the same or not. Yep.
On the test, are you going to break it down step by step like that? Or are you
Yes.
just gonna, okay.
Yes. I would break it down into individual steps, so this way I can assign partial credits. Yep.
Could you scroll down to 4 and 5 real quick?
4 to 5. Like here?
No, on the actual thing.
Oh, okay.
Thank you.
Oh, you mean step 4 and step 5?
Yeah.
Okay, there we go. Yes.
I was wondering, can you explain the difference between n and x again one more time from the previous problem?
The difference between
N and x.
n and x. Okay. So are we okay with this screen? Can we switch back to the notepad?
Sure. Or
Is that good? Okay. X is the question from step 1. Okay. And n is just my notation of the total number of tickets sold. Yeah. Are there any questions about all this stuff here? So this is the actual exam from last year. Yep.
So, is stuff like the master theorem going to be on the test?
No, master theorem is not going to be on the test because we haven't even talked about it.
Well, you probably didn't have
Yeah.
So,
I only talked about it on the superficial way because I just talked about big O, big theta, and big omega, but I never really got into the master theorem. So master theorem is definitely not going to be in the test. Mm-hmm.
Is it going to be 5 questions?
Well, thereabout. Any other questions about the test? It's open book, open notes, so if I scroll back to the description, yep, you got a
Can you
question?
go back to the...
Oh, to the notepad?
Okay. Okay.
Okay? All right. So the same rules is going to apply to that like last year? Yep.
It's on Tuesday, right?
Say again?
The test is on Tuesday?
The test is next Tuesday, correct. Okay, so let's go back to this part here. Just want to make sure that everybody understands, except for the time does not match. Okay, this is not a morning class. It is open book and open notes, no electronics. So basically the same thing as exam 1. The assessment is supposed to be individual, so we have all the usual stuff. The score should only reflect the competency of the student with the name and student ID as indicated on the top. Answers should be independently and originally derived. No sharing of books and notes during the exam. Do not discuss the question with students who may not have taken the exam, and so on and so forth. Okay, so there should be no surprises here. Any questions about the practice exam?
Can I see the... Can I see the notepad?
Notepad.
That one didn't have. Wait, so is this practice one done? Is this practice one done?
Yep. No, this is not practice. This is the actual exam from last year.
I know you went over it, but it was like after we had spent too long on like the last 2 minutes of class. But on the other one, we have the question of the coin toss.
Okay.
Is there a way that you can finish that? Like,
the coin toss. Okay. I'm not really remembering the
so the question
that
was,
question.
You have a coin toss compared to a coin. You flip it 100 times, and what's the likelihood of there being 4 heads and the rest being like 100 tails?
Okay, so we have, we need several pieces of information to figure this one out. Okay, so we start off with 100 coin flips, okay, or tosses. Okay, we want exactly 4 heads out of the 100 flips, right? So now the remaining question is the coin loaded or not?
Yes, that was fair.
Realistically, it'd have to be.
It's fair coin. Okay. So if it's a fair coin, then you have 0.5 and 0.5.
What does that mean?
A fair coin means it is not loaded. A
So one
loaded
side's a
coin.
little heavier than the other, where certain key points
50-50
still allow it to.
probability.
Oh, okay. Yeah. Okay. Huh?
So what is a loaded coin?
A loaded coin is one where one side is heavier, so it has more tendency to land on a particular side. So either it can be one side is heavier, it can also be the edge of the coin being more rounded on one side.
Or one
than the
side
other
being magnetic and having some sort of
Oh, magnetic
current
would
running in the
definitely do
table.
it, but it would be so obvious as well. The coin will fall down, and it will jump up again because of the repellent.
If you pulse it ever so quickly and it
Yeah,
hits one
but
side.
you can file the edge on one side. That would be kind of harder to see visually. But when people pick up the coin, then they can actually see that one side is kind of rounded, so it's less likely.
Had to get rid of those cheaters.
No die enemy.
No doubt.
Yeah. All right. So the question is, what are the chances that we will end up with a scenario where in 100 flips that it ends up with 4 heads? Okay. So that was the question. All right. So using the binomial distribution, we kind of know the answer, right? Because the answer is the probability of landing on a head times the number of times of a head, which is 4 here. And then there are how many ways to arrange this? It's 100 choose 4, right? In other words, there are 100 choose 4 ways to assign the number of flips. Okay, which flip gets ahead?
I don't know if this is a concept, but so I was thinking that the answer we're looking for is we're looking for the coefficient on the x to the 4th term of like 1 plus x to 100.
Say again.
Okay, so when we did the binomial thing, we had like we did this one with all the heads. You had like 1 plus x raised to.
It's 1 minus. It's x minus 1 minus x.
X minus 1.
1 minus x.
Okay, 1
but
minus
x is the probability of having a head. So in this case, it's 0.5 as well. So when you generalize this, it becomes just 100 choose 4, 0.5 to the power of 100. That's the actual answer. Yep, go ahead.
Just to be sure, that's going to be combination, right?
That's combination.
Because you don't really care about the order.
Yeah.
It's just combination because ordering does not matter.
Ordering of the 4 heads, right? Like
Okay, do you remember in one of our discussions, I said, in order to represent the result of 100 coin tosses, I can code it as a set of the indexes of the tosses that end up with a head. Do you remember that?
Yeah.
Sort of? Okay, that's from a long time ago. Okay, so in other words, this is one possible outcome. Okay, 1, 10, 99, and 100. Because that's just denoting, which toss ended up with a head. But because it is a set, it means the ordering is not important. Is that okay? So the problem now becomes, if I start with a set of 1 to 100, okay, how many ways can I create subsets of 4 out of the original set of 100? Then it's the same thing as 100 choose 4. Because ordering is not important. So that part accounts for the 100 choose 4, and then this part accounts for the product of the probabilities of which one is head and which one is tail. Yep.
What was the original question again? What was the question again?
The question is, what are the chances? Okay, what are the chances that out of 100 coin tosses that you end up with exactly 4 out of those 100 tosses end up with a head? That's the question, and that's the answer. Yep.
You only have to account for the chances of like the 96 being tail as well.
The 96
being
They're accounted by the power of 96.
Yeah, the tails are basically the 100 minus 4, which doesn't look like a 96. Penmanship.
Pretty low chances.
Yeah, this is 96 right here. Oh, now it's even worse.
Butterfly.
Okay. So without the audio, I think people would be lost. Okay, so we are running out of time. So go ahead and study over the weekend, and I'll see you guys on Tuesday.